Everybody, welcome to today's video. Today we're going to be talking about queues, and you'll see that this is a very relatively brief introduction. This video won't be very long, maybe just 15 minutes or so, just to introduce you really to the concept. We're going to look at a sample program, a single sample program from our textbook, and you'll see that it really covers, it's going to look identical, well, I shouldn't say identical, so very similar to the programs that we looked at with both stacks and then with linked lists. And so we're just modifying it a little bit to use that node structure, use that concept of a node that we've been working with to implement a queue here. So with that, we've just got a few slides I want to go through, and then we'll look at the code, we'll trace through the code, and then we'll come back and just look at a couple more things I want to explain, at least the concept here on the slide again. So what is a queue? Well, you can think of it in its simplest form as a checkout line. That is, that nodes are processed from the head of the queue, or the front, and things are added to the back. So just like when you go to a checkout line at any sort of a retail store, the first person in is the first person that will be processed out. They'll be the first one to check out, and obviously the last person that enters that queue waits in the back. Okay, this is known as first in, first out. So the first one in is the first one out. That's different than our stacks. Remember, stacks were first in, last out, because we stack on top of the stack. The first item comes in, as we add a new one, we add to the top of the stack, so we add above that value. And to remove an item on a stack, we have to pop. If we want that first value that was added to the stack and we have 15 items in front of it, then we have to pop all those values off in order to access that value in the stack. That's a little different with the queue then. We're always processing from the front. So we process from the front, we add to the back, and it's really just that simple. Now, there are several variations of the queue, and when you move into more, some of your higher level courses, so data structures and things, you'll talk about more advanced versions of these. You'll look at maybe implementing something like a priority queue, in which case you can have nodes or items or maybe packets if you're looking at a networking situation, and which can move to the front of a queue for specific reasons. Think about a theme park, right? If you go to Six Flags or Disney World, you can get the Fast Pass, and that lets you cut in front of the line. So you look at applications and when you can do that in later classes. Again, just a soft introduction here. Applications, a lot of different applications. If you're interested in those, you can certainly find a lot of resources on the internet to help explain that. Print spooling, usually that's a pretty good one. Jobs come in, jobs go out. The first one in is the first one out. Packets traversing a network, typically the same process. All of our hardware out there typically processes traffic in a first in, first out type of an order. Okay, sample program, queueintro.c has been uploaded to D2L. If you do not want to download it from there for whatever reason, you can also find it from the book. Okay, so this is another one of those sample programs that I'm taking straight out of the book, and I'm mainly doing that in order to help, because then this code, not only do we have our time in this video to go over the code and review it, but the author also does it himself, so you can at least have a couple different perspectives when looking at the code and getting an explanation if you're struggling with anything. If we open up the file, then you'll see it's a relatively large file in terms of the program size that we've been working on this semester. But again, a lot of this here is exactly the same concept, almost the same code. There's just very few minor modifications to it. So here we have our struct. We're calling it a queue node instead of a stack node, or instead of the, I'm just drawing a blank now on what we call them in the linked list. But same concept. We have two members. One's a self-referential pointer, and then the other is the char member to hold our data. So with this one, you can see with this queue structure here, we're going to hold chars. We have a couple of different type definitions that we'll use throughout the functions. Again, almost the exact same, except we're just changing the names here. When we talk about adding and removing from the queue, then we talk about, or we use the terms enqueue and dequeue. So enqueue means we add, dequeue means we remove. And you see we have these two function definitions for there. From there, we have print queue is empty and instructions, right? And again, those are all very similar to what we saw in the previous programs that we looked at. Okay, first thing, as we get into main here, you'll see probably the biggest difference is we have, instead of just one single pointer keeping track of one element of of these data structures that we're using, we actually have two. Okay, because we need to, when we enqueue, we add to the back. When we dequeue, we take from the front. And so we have to have two pointers in order to keep track of what's at the head and what's at the tail. When we remove, we'll modify from the head pointer. When we add, we'll modify from the tail pointer. So we have two pointers in this case in order to help us keep track of that. So that is one difference from when we looked at stacks and linked lists. From here, very similar setup. We have some items for the person to enter. We have a choice for this very simplistic menu that we have. We print the instructions. We print that question mark just to indicate that the program is ready to accept user input. Then we have a scanf, and we enter this while loop. All right, so then this just enters the main functionality of the program. Okay, from there we have our switch. Case 1 will enqueue, case 2 will dequeue, and then we just have a default case here to catch all others in case they entered something invalid. Once we've gone through that switch, prompt them again for the menu option. As soon as they enter option 3, we have the end of the run. If we look at a couple of these functions then, you'll see here's our instructions, very simple, just a printf with a bunch of statements for the menu. We check if it's empty. Okay, very simple check. We pass the head pointer, the value of that pointer, to this function, and if it's equal to null, then we return null. We return, we don't return null, return 0 or 1. Does this evaluate to true or false? And we use that with a basic primitive integer type. All right, so, and then let's look at print, which I think it's down here, and here we go, at the bottom. Again, it's going to look very similar, if not identical, to the print list and print stack options that we looked at previously. So first we check if the pointer, this should be our head pointer, if it's empty, if it has a null value, then once empty, and we're done here. We just print that the queue is empty. Otherwise, we print the queue, and then we're just going to use this while loop to walk. Again, it's at the core, it's a linked list, and so we're just walking these nodes. We're saying, well, current pointer is not equal to null. We need to have a valid memory address in order to start traversing through this queue. We print the value of the data member, and then we set the current pointer equal to its next node or its next pointer member, which in case then we walk until we get to the very end. Just like the other data structures that we looked at, queues, the tail of the queue, its next pointer, in this case, the next pointer member is going to have a null value, and that indicates that we've reached the end of the queue. Okay, so again, all this should look very familiar to the other functions, the other programs that we looked at. If we go through execution of this program then, let's first take a look at case 1, in which case we want to add an item to the queue. So just got some enter, we prompt the user, enter a character. We have a scanf here, and add the item. We then have enqueue. We have the head pointer, the tail pointer, and the item that we want to add. Okay, so remember that when we started, we set, in this case, let's say it was the first time through this program, both of these are equal to null, head pointer and tail pointer. Okay, because when we enqueue and dequeue, we want to keep track of those. And so we need to pass both of those values, both of those pointer values, to this function. Okay, so we enqueue. Let's say the user entered a value. This will be the item. They entered a char value. Now we're going to enqueue that. Okay, so here's our function. We're adding an item. So the first thing we need to do is create a new node. In this case, a queue node. Okay, so queue node pointer, new pointer equals malloc size of queue node. Okay, so again, very similar syntax here. We're just mallocing memory for the queue node. If it's not equal to null, okay, what can malloc return? You saw that in one of the quizzes that we did. It can actually return one of two things. It's going to return the memory address for the allocated memory, but if it was not able to allocate the memory, then it can return null. So we're checking that right here. If the return value that was assigned to our new pointer, as long as it's not equal to null, that means that we had the amount of memory that we requested here, it was allocated to us, so that we can go ahead and access the members of this object or of this structure. If it is equal to null, then we just couldn't get the memory. So we print off a statement and we don't actually enqueue. From here, very simply, we update the data member, we set it equal to the value, and then we add, or we set its next pointer equal to null. Okay, we don't have to change this because we're enqueuing, we're adding. We're always with this particular program, because this is a simple first in, first out queue. Whenever we add a node, it's always going to be at the end. So we always have a new tail for our queue. All right, so that member is always going to be equal to null. All right. Now, though, we need a test. Okay, right now our queue is empty. Right, this was the very first time we've inserted an item, and so we check: is the head pointer empty? If the head pointer is empty, then we have a new head queue or a new head node. Not only is it the head, but it's the tail. And so you'll see here in a second that we're going to update. We're going to update the pointers to point to this one single node, so they're both going to point to the same memory address. So in this case, if this was our first run through this, it would be empty, and we would say head pointer now equals the value of our new pointer. So it's now pointing at the new pointer. If it's not, then we pass the tail pointer to the applicator, to this function. So we say that the tail pointer's next pointer member, previously it was pointing at null because it was the tail node. Now it's pointing to the new pointer. We just added this node to the end of the queue. And this is us linking the previous tail node or the previous end of the queue to this new one. And then finally, regardless of what happens here, this is really just making sure that we link the appropriate, whether it's a new head or if it's just linking to the end. The last thing we do is we update the tail pointer and we set it equal to our new pointer, the new node. So now we've linked it here. We've either created a new head node or we've linked it and now we have a new tail node. And then we always update the tail pointer to point to that last node, that last item that we just queued. Okay, so that's what that function does. All right, if we go back here, and then once we're done, we'll print the queue. We'll see that here when we run the program in a second. All right, case 2 is going to dequeue. We can't dequeue an empty queue, so first thing we do is we check if we're not empty. Okay, so logical negation here. If it's not empty, we can dequeue something. If it is empty, we don't even want to try to dequeue because we probably run into errors there with the segmentation fault. So we have an item variable. That's going to be the item. That's where we're going to store the value from dequeuing. So if we look at the dequeue function, we can look at the prototype and see that the dequeue returns a value. Okay, remember, we're removing an item, just like with the stack. When we remove an item from the queue, well, when we remove an item from the stack, it's no longer going to be there. So if we don't store that value somewhere, then it's going to be gone and it'll be kind of pointless. Same with the queue. We're going to dequeue it. It'll no longer be a part of the queue. It'll go away. And so if we don't return it and store it, then we won't really have any use for it. We won't be able to use that value. So with dequeue, we only have 2 arguments, the head and the tail. Okay, we're going to remove an item, so we need to make sure that the head and the tail both point to the appropriate place. The return value will be stored in this variable, and then we'll simply print that off. All right, so let's take a look at our dequeue function here. Okay, so inside of the function, return type is char. Return type, we have to return the same type. So this value has to be a char value, in which case here it is. So we have this variable declared. That's where we're going to get the data member from the node that we're going to dequeue. We're going to have a temp pointer. We're just going to use this as just like we did basically with the stacks and the linked list. We're going to use that to temporarily hold a memory address so that we can deallocate the memory. So we set value. Okay, dequeue, taking from the front. So we're setting the value equal to the head pointer's data member. We then say that temp pointer is going to point to head pointer. And now head pointer is pointing to its next node member. Right? This essentially is allowing us to take that head pointer and point to its next node member, so the next item in the queue. But because we just changed the value here, we had to set the temp pointer equal to it. So that way we can deallocate that memory. We can't deallocate that memory until we've made this assignment. But if we make this assignment, then we lose the value that head pointer was pointing to. So we go ahead and do that. Okay, remember we want to free with any memory that we've allocated with malloc. We always want to free it when we're done. Once we've done this step here, this essentially updates the head pointer to the next node. So now that item's essentially been dequeued from the front of the queue. If the head pointer is equal to null, then the tail pointer needs to equal null as well. Right? So that's just saying, we're just making sure that if the head pointer is equal to null, that means we only had one item in the queue. We've just removed it, and so now our queue is empty. And so we need to make sure to update tail pointer as well. If we called this with one item in the queue, head pointer and tail pointer would be pointing to the same location. So if we did not do this step, tail pointer would be pointing at a memory address that we're about to deallocate, we're about to free. In which case then, if we try to access that value, we get a segmentation fault because it would be pointing at a memory address that has no longer been allocated to our program. Okay. Once we do that, then we're done. We free temp pointer. We have that memory address that was the original one for the head of the queue. We stored it in temp pointer right here. Now that we're done linking our head pointer to the next item in the queue, we can go ahead and free that up, which is what that call does. We're done. We'll return the value that we stored from the data member of that head item. And in this case, all we're doing with that value is printing it off. So you can see a printf to do that. And then we print the queue so that you can see that it has in fact been deallocated. Okay, so now if we go ahead and we'll run this program. I've already compiled it. Enter your choice. Okay, so we want to add an item to the queue. I'll choose a menu option 1. We entered A. And then you can see there's our queue. So it's A and then null. Remember, just like with the linked list and the stacks, null indicates the end. In this case, it indicates the end of the queue, the end of our series of nodes. All right, let's add another character, B, and let's maybe add one more, C. You can see beginning of our queue, A, end of our queue, C, and as we're adding, the items are just coming in behind. So if we want to go ahead and dequeue an item, A has been dequeued. It doesn't give us the option, which item do you want to dequeue? It doesn't matter. I don't have a choice because it's going to come from the front of the queue. So we've dequeued one item, it was A. Now our queue is B, C, and then that's the end of our queue. If we add an item, let's say I want to add A back, okay, A goes to the end of the queue. So now we have B, C, A. So if we want to get that value off of there, then we have to have a couple of dequeues. We can remove the last item, okay, and the queue is empty. So we can go ahead and we can continue to try to dequeue an item, but that doesn't exist. And so the logic in the code, which we just looked at, is stopping us, preventing us from doing that. We can add another item, add A, and we're good to go. And now we're just adding items to the queue. First in, first out. New items go to the back. Removing items comes from the front. Okay, and then 3, and we're done with executing the program. All right. Let's see, I'm going to go through that maybe one more time just to give you a slightly different explanation here, just in case there was any confusion or maybe uncertainty or I wasn't clear exactly by tracing through the code. If we look at this function then, okay, again, we have head pointer and tail pointer. And let's just say that we have what's called head pointer and tail pointer. Okay, and right now, both of these are, let's just do something like this, both pointing at a null value. Okay. If this is, again, we're assuming that our queue is empty. So the first time through, we malloc memory for a node. So I'll just use these rectangles to represent that. This will have some sort of a memory address here. And I'll just create something arbitrary, and let's say that the user wanted to enqueue the letter A. New pointer, so I'll call that NP, is now pointing here. Okay, so that mallocs the memory, which is this step here. We'll assume that we got the memory, we've updated the data members. Its next node, it's pointing to null as well. Okay, and that's good. We've updated that with this statement right here. We check, is the head pointer empty? In this case, it is. So what do? Let's change the color to, how about yellow? Is empty head pointer? Head pointer is equal to null. So now we're going to update that. Head pointer equals new pointer. What is new pointer pointing to? Right here. Okay, so now we have our head pointer pointing to that memory address that we've just been allocated for this node. Okay, tail pointer equals new pointer. So we've gone down this branch in an if else. That means we're not going to execute this branch here, not with this pass through this function. And now we update the tail pointer to the new pointer as well. So in this case, tail pointer was pointing at null, and now it's pointing to the same location. Right, and then we're done. And that's simply all we have to do. Let's see. Let me erase some of this. I'm sure I can, but I don't know how to do that offhand. So if we updated or added a second item, I'm going to try to do this. I'm not sure. I might get the screen just a little too cluttered here. But let's say that we update a second item, and we want to enqueue the value B. We have this current setup. Let's change the pen color here to green. And let's say now we're passing through this a second time. Okay, we're adding a new node, so we're going to malloc memory. So we're going to start here. We're going to update the data member, and then we're going to set its next node member equal to null. We have to have an indication when we're at the end of the queue. Okay, we have some sort of memory address here as well. Something random. All right, we check, is the head pointer empty? In this case, it's not empty because the head pointer right here is now pointing at this node. So what do? We update the tail pointer's next pointer equal to the new pointer. Okay, so because we don't need to worry about the head pointer, we're in queuing. Head pointer needs to stay pointing at the front of the queue. We update the tail pointer. So what do? We access through the tail pointer, which is pointing at this node, we access its next node member, and we update it. We say that it's now pointing to, in this case, on this pass-through, this is our new pointer, right? It's pointing here. And we update it, and now it points here. So thus we've linked the item. So now it's the second item in our queue. We have a relationship between the two. So as we traverse those next pointer members, we can go from this queue item to this queue item, or this queue node to this queue node. And then the last thing we do here is we say that the tail pointer equals the new pointer. Okay? So now we update this link here, and it now simply points right here. All right. So hopefully that made sense. I apologize, this got a little cluttered, a little more cluttered than I wanted, but my lack of PowerPoint skills prevented me from erasing some of these things. I'm sure it's pretty easy, but I just didn't know. Got one more slide. We'll go through this one real quick. And it's just this is the dequeue process. So it's just the same, or just the reverse of that. Let's go ahead and go with blue. And let's say that we have, a single item in our queue right now. That'll be A. We'll have some memory address here. Remember, its next node pointer is pointing to null. Oops. Okay. And then we'll have it's a bad color choice. Let's try green. We'll have the tail and the head pointer. And because we only have one item, they're both going to be pointing to here. Okay. We're also going to have a temp pointer. So I'll just call that temp. And what do? Well, we have value equals the data member. So if we have our value variable, we'll set that equal to A so that we can have that value to return later. Temp pointer equals head pointer. Okay, so if this is our head pointer right here, it's pointing to this node. So we point our temp pointer at that node so that that memory address is stored there. We now say head pointer equals head pointer's next pointer. Okay, so that updates our head pointer. Let's try magenta. It's no longer going to point at this node, it's going to point to its next node member, which is our null value. Okay. So we have to do a check. If head pointer is equal to null, which it is, because now there are no more items in this queue. If we didn't do this step, tail pointer would stay pointing at this memory address, and we're about to deallocate that. So in this case, we've now emptied the queue, so the head pointer equals null, so we update tail pointer equal to null. So we break that link there by updating the value, and now head pointer is null, tail pointer is null. That's valid because we have an empty queue. We need both those values to be empty. We're done with this statement, and now we free, because we saved this memory address in temp pointer, because had we not done that, we would have lost those values when we pointed head and tail to that null value. We can free it. So now we've deallocated it, and now this node is gone, it no longer exists. Here's our value, and we can return that. If we had multiple items, and I won't go through it because I'll just make a mess of this screen here, but if we had multiple items, the only thing that would change is that when we make this link, when we say head pointer equals head pointer's next pointer, we would set it equal to the memory address of the next queue node, in which case then head pointer right here would not be equal to null. So then we would never update the tail pointer, because we don't have to. The tail pointer in this case would have been, if we have two items, the tail pointer would have been pointing at that second node, so we don't need to do any updates. Okay, so that's our introduction to queues. If you have any questions, as usual, please don't hesitate to reach out to me, send me an email or something and let me know. Otherwise, that's it for today. Talk to you guys later.